Alright, time for another DraftPhysics.com video presentation. So I think I'll change of pace, go back to photons for a video. So, Huygens Optics has made a video, and he's again kind of trying to argue that the wave theory of light and defend it. And he won't defend it in any kind of back and forth way. I mean, you can't really argue the argument because he won't participate in the argument, unfortunately. So it's just a propaganda thing. He says his bit, I guess all I can do is say my bit, and there won't be any response to the arguments, the counter arguments made. And that's the way it's just going to have to be. And whatever. Commercials. Yeah, whatever.
In the lens pattern.
Okay, so somewhere here we have to deal with this crap. Blah, blah, blah. Physics videos have to have commercials on them. Just has to be that way. Alright, now I think this is the right location. I hate to change anything, but I'm going to play another commercial. Simple enough. Okay, so then he's making some argument about spatial dimension of the lens. I don't know if that's the important one, but we'll play from there anyway. I'll make sure that's visible. Good enough. Alright, probably could use a little better volume. So I'll move this up. And move this one down. That should fix that. One can hope. That's right. And press the button. Yeah, mouse needs a recharge.
Lenses with the same focal length. Why is it that the one with the smallest diameter or opening angle is fundamentally less sharp? All these questions are in fact quite hard to explain at a
Alright, so obviously it's less because it's less information. So the fact is the photons are a standard size. You're using less volume of photons, so obviously you're going to get less resolution. The photons aren't going to be as many, and therefore there's going to be less information to rebuild the image out of. That's a simple answer. Good enough for me anyway. So in the whole image is going to be in a smaller amount of space. So, you know, any kind of deviations or irregularities and any imperfections in the angles or anything like that, it's all going to show up as because you're compressing the information. Compressing. Relative to the size of the image. You're forcing a bigger image to fit in a smaller space. That's the problem. Simply put.
fundamental level if we view light from a ray perspective. Now, most of you will of course know that light isn't actually rays, but electromagnetic wave energy.
So again, why would we know that? There's no videotape of it, there's no photographs of it, there's no anything. There are arguments that are pretty sensible saying, well, if this B field exists, if it did have something called the magnetic field, then you should be able to bend this stuff with a magnet, and you can't bend it at all. And frankly, there's no evidence it's even really bent by gravity, frankly. So, why say this? I mean, there really isn't any evidence for it except for the fact that it satisfies your imagination, but it doesn't really satisfy any physical facts. To give it these two properties, it doesn't need them.
And light in the visible wavelength range very much behaves like a wave.
Says you. So again, I would argue that every instance where you make these comparisons, you're cheating, you know, and that's just the truth. You're saying it looks like or it seems like, but it really isn't that much like. It doesn't fit the pattern really at all. Waves do interfere with each other in a real physical way, and it can be demonstrated that these waves don't. Just again with a simple radar experiment where you just send a signal from two opposite sides, and you can create interference even though the two signals never meet. They never see each other, yet they're interfering with each other, quote unquote. They're creating a fringe pattern. Now, it doesn't make any sense. If they don't need to interfere in the space, then is interference realistic?
What rays are trying to depict is the local direction of wave propagation, And so to understand,
Yeah, again, so that doesn't even, whatever that even means, right? We know that they're propagated as, frankly, vectors, rays, and every drawing you draw, you're still stuck doing that, putting vectors inside of your little lumpy images, because the fact is it's vectors.
why light really behaves the way it does, we should actually be looking at how waves behave. Let me just show you a wave animation. It features 2 point sources that emit waves at a fixed wavelength. Furthermore, we have a lens, which is an area where
Let's see. Well, I think
the waves propagate much slower and which has 2 curved surfaces. And on the right side we have a plane where this lens focuses the wave energy. Now these lines show the ray representation of how these 2 sources are imaged onto the image plane. But this is how it looks from the wave perspective. As you can
Okay, says him. So this is them doing their mathematics, whatever it might be, to create this simulation. So nobody told us what exactly this simulation is duplicating, and so by what math it's even using to create this illustration simulation. So he did say there was a whole part in here where he's saying it can't be a wave because, it can't be a ray because, so I guess I was too late for that part, so I had to go back further, unfortunately, so we'll go back further.
of the physics that's going on. Now let me give you a few examples where rays completely miss the point. For example, why in the first place would a ray change direction when entering a medium with a different refractive index?
Because the force is actually going to be converted in the sense that it's not going to be free anymore, like in air or a vacuum. You could argue it's relatively free. It doesn't hit too many atoms, doesn't communicate by being transferred from atom to atom. When it enters the material, that's what it's going to have to do. It's not going to be freely flying through the material. It's now going to be passing from electron to electron. It's a very unempty space it's traveling through. So it's kind of simple to draw a diagram of why it would tend to bend, and it bends its surfaces. It doesn't just bend anywhere. It bends at this particular point, the surface. Alright, and so it's pretty easy, in my opinion, to explain why something might bend at a surface. So I will do that. Oh, this mouse is going to be a pain in the ass. I guess I have to fix this. Yeah, let me fix it. Or actually, I'll go crazy. Pause.